Please welcome Katherine.
Thank you, Mark, for that nice introduction, and thank you everyone for coming. I am Katherine Kuchenbecker, and it's really an honor to be back. This is a homecoming for me to come back to Penn. Actually, I used to teach on this stage for MEM 211, and I'm really happy to be here in person and virtually to share some about the research that my team and I are doing. So let's see if this will go forward. Let me know if there are any technical problems like this one, where we're not moving forward when we want to go forward. And we'll try to see, can we go back? We can go back, we can go forward. So today I am giving a relatively broad talk. I want to give you a little bit of an overview about two big fields that I work in, haptics and physical human-robot interaction. And for each of them, I chose a picture of my most recent two PhD students with their doctoral dissertation. And they're actually both have connections to Penn. So Eric Young was my last Penn PhD student, and he created the 6-degree freedom fingertip puppeteer device. On the right is Alexis Block. She was my first PhD student in Europe. She was a Penn undergrad MEM and Robo Master student who moved with me to Germany, and she made HuggieBot. So I'll be telling you about their work and other work, but I just wanted to explain, like, Penn is very important to me. How did I get to being where I am? Well, I grew up in Los Angeles. My parents had gone to UCLA for graduate school, and I did all my degrees at Stanford University in Northern California. Because I liked teaching and working with students so much and coaching them on projects, I decided to get a PhD. And I found a PhD advisor. I was his first student. His name was Günther Niemeyer. He had done his PhD at MIT. And together we worked on teleoperation, haptic feedback for teleoperation, and also for haptics. And I'm really grateful for the mentorship he provided me. And then I interviewed for faculty jobs. I interviewed at around 16 universities, including Penn. And I was so excited about what I saw here in the GAS lab, Mark, DJ, everyone else, that I accepted the offer. And Penn was also kind enough to let me delay my start by 1 year. And I just want to say thank you. That was really helpful to me. It let my husband finish his PhD. He was also a Stanford PhD student at the time, and it let me gain a little bit more experience. So I did a 1-year postdoc with Alison Okamura at Johns Hopkins. She's now at Stanford. And was like driving up from Baltimore to Philadelphia to like look for houses, work on lab renovations, recruit students, plan my first classes that I was going to teach here. And then, yeah, we moved here to Penn in July of 2007, and I was here for 9.5 years because I got an opportunity to, and I was part of the GAS lab. I had a secondary appointment in computer science. I was in the graduate groups of bioengineering and electrical systems, and had many wonderful friends and collaborations. I'll talk about some of them later. And then, yeah, in January of 2017, we moved to Germany. We moved to the Max Planck Institute for Intelligent Systems. The Max Planck Society is something you might not have heard about much because there isn't much in engineering research in the Max Planck Society. But it's a set of more than 80 institutes all over Germany and a few abroad that are funded from taxpayer money. And Germany is really investing in basic curiosity-driven research. And they're very generous. They give us really good conditions for doing research. And I'm part of an institute that's in southern Germany that has 2 sites, Stuttgart and Tübingen, and it was founded in 2011. And these are like all the faculty in my institute. So across the top are directors like me. So we're like full professors who will be there for the rest of our careers. Hi, Kostas. And along the middle in the circles are our group leaders. So they work with us for like 5 to 9 years, and then they go out and get a tenured professor position elsewhere. We're doing research all across robotics and artificial intelligence, computer vision, soft robotics is a big theme. And we're hiring at all levels. So I only say this not to try to steal people, but to show opportunities. So if you have a postdoc, or if you're a PhD student, you're looking for a postdoc, or a postdoc, you're looking for a group leader position, or you're a master's student, and any of these things, we have open director positions. We're hoping to hire something like 18 new group leaders in the next few years because we got a big grant for an AI center in Tübingen called the Tübingen AI Breakthrough Hub. And so if you're interested in these kinds of things, interdisciplinary, and it's really a wonderful environment to do research. The PhD program that I run that Mark was mentioning is called MPI-IS, International Max Planck Research School for Intelligent Systems. And it's very interdisciplinary. I really am grateful that Max Planck embodies a lot of the things that I enjoyed here at Penn, of interactions between people in many different fields. So yeah, if you're ever in Germany, let me know or come visit our institute, and we would love to show you around. My team, these are people who work directly with me. I currently have too many PhD students, but I really like all of them. So about 15 PhD students, 4 postdocs and recent postdocs, who are now working in faculty jobs and have lots of visitors and some central staff. And I'll be showing you some of their research today. I also wanted to show you, this is a picture of everyone who ever worked in my lab when I was here as a professor at Penn. So across the top are my Penn PhD students and postdocs, and then master's thesis students, other master's students, medical students. Lots of undergrad researchers along the bottom are my main faculty collaborators. Yeah, and I just want to say I also worked with Max Mintz, and I was really sad to hear of his passing. And he was very special to me. We have a paper together. He was a wonderful mentor to me as a young faculty member. We ran an REU site, the GRASP REU site, and I, through running that REU site, really learned a lot from him and from how he worked with students. So several of the students up there were in our REU site, many undergrads. And he also had a very special role for Heather Culbertson in the top middle, who's now an assistant professor at USC, and also Alexis Block. Yeah, so we will miss Max. When they made Max, they broke the mold. So a lot of the motivation for our work, although we work in many domains, and today I'll only be talking about 2 of them, a lot of the work we do has some underlying motivation about the sense of touch. And so perhaps you think your sense of vision is most important, or you really appreciate hearing or taste or smell. Those are all nice. But I want to convince you that touch is really crucially important, and especially for physical interaction with the world and with other people. And so it's fundamental for us, also for animals. It's the first sense to develop. It's extremely difficult if you happen to be unlucky enough to lose your sense of touch. It's extremely, extremely difficult to still function in the world. It's because it is deeply coupled to action. So as you reach out and move, if I want to push this button or pick up something or brush my hair or put on my clothes, your sense of touch is constantly giving you feedback about what you're doing in the world and helping you correct and get the action that you want. And it's also deeply coupled to social interaction with other people. And unlike vision and hearing, which are localized, our receptors for touch are spread throughout our body. And it's actually many different kinds of measurements that our body makes about our body and the world around it. And so I'll teach you just a little bit about what you need to know about the sense of touch. I would split haptic stimuli into 2 main categories. The first would be tactile or cutaneous stimuli, things you feel directly in your skin. Where is something touching me? Is it pressing? Is it stretching my skin? Is that thing slipping along my skin? Is something vibrating either on my skin, or especially if I'm holding a tool and I'm tapping an object or I'm cutting things and dragging, you can feel vibrations up to 1,000 hertz. Much, much faster frequencies than you can control in closed loop motor control. You can feel exchange of heat, and you also have a little bit of proximity sensing in your hair follicles. Receptor density of these changes across your body. So your fingertips are very sensitive and other parts of your body are less sensitive. Now that's the surface of your skin. You also have the deeper network, your kinesthetic or proprioceptive senses. And this works by, you can feel the lengths of your muscles and whether they're extending or contracting, and the forces in the tendons and different ligaments around your body. And there's a little bit of like joint angle receptors, not like encoders on robots, but something a little bit like that. And your body, your brain, your nervous system is constantly fusing all these different sources of information to give you an impression of how your body is moving through the world, what it's touching, and whether you're having the impact that you want. And so, and I think especially like when I started as a PhD student at Stanford in around 2002, almost everything in haptics and robotics was all about kinesthetic, like motion. And increasingly over the years, I think the tactile side of things, whether that's giving robots an actual sense of touch or paying attention to the tactile cues that a user might feel, is growing in importance, and I think is a really nice, the other half of the story that was often being ignored. And it's a key to success in such systems. So your sense of touch is really important. Do you believe me now? Okay, good. It is. I'm glad. But most of the engineered systems that we use every day or that are built don't take advantage of the sense of touch. And by that, I mean, they give us beautiful visual stimuli, some audio stimuli, and only a little bit of things that we can feel. Now, touchscreen devices feel us. They know where we touch them, but they don't present different sensations. So this is my cat, Toby, who came from Philadelphia. He cost $1 at a shelter here in Philadelphia. He likes Germany very much. But when I touch this picture of my cat on my phone, I don't feel anything. It just feels like glass. I can't shop and touch different materials and feel what they might feel like. We don't have a good way to digitize how things feel. That happens also in virtual reality. We can move around and manipulate, but the cues that we want to feel there, they're just almost nothing, or they're very encumbering. I've done a lot of work on robotic surgery. My PhD advisor had been one of the first engineers in intuitive surgical. This is a system where the surgeon sits and can remotely control these tiny little robot hands, but it's done completely with vision. There's basically no haptic feedback, and that makes it much more difficult to be delicate and to control your interactions well. They still operate on people every day using these robots. I think the lack of haptic feedback is part of why they haven't delivered on the promise that this technology everyone hoped it would have of revolutionizing surgery. Robots very rarely have any tactile sensors, or they're very primitive. This is graspy, or this is pHRI. This might be one actually not graspy, but at Willow Garage, I think, but from the same era. And yeah, they have very little in terms of touch, and social robots on the rest of their body basically can't feel anything. They might have bumpers on their toes, or a little binary sensor on the back of their hand, or on the top of their head, but really minimal. And so I see the mission of my lab overall. We're working to bring physical interaction and touch cues more to the forefront, to take advantage more of that modality to enrich user interactions and give robots new skills to interact with the world. And yeah, so today I'm going to be telling you about haptics and physical human-robot interaction. Other things my lab worked on, we do a lot on tactile sensors. I just gave a talk at MIT last Friday where I talked only about our tactile sensing work. It's on YouTube. You're welcome to watch it if that's interesting to you. Also on autonomous robot manipulation and learning for tactile sensations and fingertip interactions with touchscreens. But today we're going to talk about these two domains. And for each one, I'm going to try to give you a little bit of an overview of the field, then quickly show you some sample projects, and then go into depth on one detailed example. And we'll start with haptics. So a few years ago, I got asked to write this encyclopedia article for the Springer Handbook Encyclopedia of Robotics on haptics and haptic interfaces. And it was really nice. I used to teach a haptics class here at Penn. And I used this article to try to describe how I think about haptics. And so I'll try to explain it really quickly. This is the most classic haptic device. It's a grounded force feedback device, like a back drivable robot arm, a Phantom. This is the most cited paper in haptics by Massey and Salisbury from 1994. And when I had the experience of starting to use these devices when I was a PhD student, I had the simultaneous impression of, wow, this is so cool. Like you could program a sphere or a flat surface and you could feel virtual objects. You basically program the geometry, you make a virtual spring. So cool. And simultaneously, it really sucks. Like it feels nothing like a real object that you touch. And so it's somewhere in between feeling nothing and feeling, you feel something, but you don't feel something realistic. It doesn't match what I feel when I touch things in everyday life. First, it's tool mediated, but even for only tool mediated interactions, it wasn't as rich or as crisp or as expressive as real things you could touch. And so that made for a good PhD. And it was actually this attention to higher frequencies that was really missing, why everything felt soft and squishy and unrealistic. And so we can use devices like that for two main things. One, to control a robot in a remote environment. And so here I am as a PhD student, remotely controlling another Phantom to tap on objects. And I had put an accelerometer on the remote robot, and then I was using the motors to apply the high frequencies so you could really feel the difference between hard plastic and wood or different materials. But normally it's just done with a spring, even though we want to make them match really well. And then the other big thing, we can touch virtual objects programmed as geometry. And again, this is actually a class demo or homework assignment from the haptics class I used to teach here. I had my students program different haptic effects. They could feel friction or texture or negative friction or different softnesses in the middle. And it's really nice. We want it often, we do want for different applications. Maybe we want to do medical simulation or design. There are many different applications where these kinds of technologies are useful. And again, we often use just like some sort of a spring, which again, the high frequency information is usually missing. So the kinds of haptic interfaces that are developed, I've been showing you so far grounded devices that sit on a desk or on the floor and then can use that grounded connection to push off and push back on you. So you're back driving the device, moving it around, feeling things. That's the first category. The second is just wearable or ungrounded devices that are pushing back on your body or only vibrating. And then there are a lot of screen-based haptic interfaces as well. Sometimes there are some hybrids. no matter which of those three categories this haptic device is in, the way I think about it is it's a mechatronic system that's trying to mediate, trying to modify my interaction with the world around me. So it has some sensors, so it knows what I'm doing. It does some processing, it gets some data from the remote environment or from the virtual environment, and then it's trying to respond back to me with some actuation through these layers of mechanical, electrical, and computational really fast to try to make it as though I was touching a real object. But I always feel the device itself. So you're always trying to trade off the encumbrance of the device and what I feel. You want that device to be as quiet and as clean and lightweight as possible so that the content, what I want you to feel, the virtual surgery or the 3D object, the texture of the fabric you're thinking of buying can really pop, and I can feel that and transmit that very accurately. Yeah, I think that text says some of the things I just said. It's this, we're modulating my interaction between me and the surroundings around me. And we're often trying to imitate what a real interaction feels like. So I'll show you some sample projects. These were almost all done at Penn or started at Penn, and we'll go in series. So at the upper left, I was working with my second PhD student, Will McMahon, and Ted Gomez, who was a Penn medical student, who did a master's in translational research with me. Will and I and others, we invented a way to add haptic feedback to the Da Vinci system. So we add little accelerometers, vibration sensors on the instruments under the sterile baggie, and we take those vibrations and transmit them to the hands of the operator so they can feel when so those are the little orange 3D printed clips near the surgeon's hand. And when the right tool feels the vibration, the right surgeon's hand feels that immediately. And we've done tons of research on this. It adds a lot of realism and changes your learning curve. And so letting you feel what the robot is touching is beneficial. And then we validated it in surgery. This is a pig, not a human. Surgeon, my surgeon collaborator, David Lee, operating on an animal, and we're able to show we could measure these signals. The surgeon could feel them. Here he's cutting a vessel after he tied knots. And the sounds you're hearing are the vibrations we're measuring on the right and left field. There are nice transients when he's cutting and clipping. And so that was a very simple technology for adding haptic feedback and very effective. On the lower right, this is work led by Claudio Pacchiotti, who was a visiting PhD student with me at the time here at Penn. So we took a BioTac, a fingertip sensor that is mostly sensing deformation and also vibrations. And then we're feeding those sensations back to the surgeon's finger, the operator's finger. There's a rigid rod embedded in the soft tissue, and we found that this kind of feedback, you can feel like the tangent plane and the pressure and the vibrations really let people, almost like bringing your finger inside the patient. It's not ready to go for testing on animals or humans, but it worked quite well. And then at the bottom right, this is actually a video from the Grass Lab. This is work led by Rebecca Pierce-Kershid. She did teleoperation for the PR2, but now no grounded force feedback, just a wearable device. And it has grasp force feedback, vibrations, and making and breaking contact. And the user's task was to manipulate objects delicately and set them down. And we showed that both the grasping feedback and the vibration feedback made people more delicate, more careful, more effective in the manipulation. Those were some teleoperation examples. Now we go into virtual environments. These were wearable devices that we developed for guiding the user's motion that try to emulate how a person might tap or squeeze another person. This was work led by Andrew Stanley, who was a meme undergrad who did his PhD at Stanford after working with me here. And we could guide human motion. Normally, vibration motors are used for things like that. And this is work that Joe Romano started and Heather Culbertson finished, or both worked on a lot. We're capturing, we would drag a tool over real surfaces and measure the vibrations and then play them on the glass through a little vibration motor. So the actuator is the same as what we showed on the Da Vinci robot, but now instead of the signals coming in real time from the measurements of the instruments vibrating, now we generate them, we synthesize in real time. And actually this is the project that Max Mintz worked on with us in signal processing. So we basically make a little model of how the texture feels when you're moving at a certain speed and pushing with a certain force. What's the spectrum of the vibration that you feel? And then as the user's moving across, I'll show the next video. This is Heather's, like the final demo from Heather's dissertation. Now it's in 3D, also with friction forces and hardness cues. And again, we have that little voice coil motor, which is basically like a speaker, a magnet in a coil that can shake back and forth and give you the feeling. She captured 100 textures. This is a big database, the Penn Haptic Texture Toolkit. And you can feel all these very rich and realistic textures in real time and move however you want. And it's quite compelling. And then the last one, this is Eric Young's PhD. He started here at Penn and then finished it in Germany. He made this crazy 6-stop continuum manipulator. So we have 6 rods that can extend and contract and control the 6-degree of freedom pose of a platform at the user's finger. And then we use motion tracking to know where you move. And we can give you the feeling of touching, like making and breaking contact, the pressure, the shape, so the tangent plane, and also the friction, translational and rotational. So he did a lot of engineering to get that worked well. And then we had a Kai paper last year where we tested it in different applications in virtual reality. Yeah, and then this was another one you had to you had to blindly feel these surfaces and guess the curvature, and then also move a little object around and guess if it's heavier or lighter. Right, so those are fingertip haptic devices. It is not as easy to give a talk wearing a mask. This is like going running. I'm going to keep just breathing and try to articulate and breathe deeply. So those are a bunch of haptic devices that my team has made. We've made many other ones. There are many others in the world, but at least it gives you a sample. I'm sorry I can't show you any demos, but maybe you get an understanding of how these things work. And now I'll give you one detailed example, and this is all work I did after I left Penn. So as you can see, there are tons of haptic devices. Who can keep track of them? Which one is good for what? How can I even compare them? It's still pretty early days. People's making this and that. They're 30 years of inventions, but sometimes people don't know what came before. And a lot of now designers want to use these devices to create experiences, people who aren't necessarily mechanical engineers who would design and build it. And so we created what we call Haptipedia to solve some of these problems. So one problem is like you have to read papers. They're buried in the literature. And you really have to have a high degree of understanding in order to really understand from a paper what was special about this particular device and how it performed. The research in this domain started in the 90s, and a lot of the older papers are hard to access, or we lose touch with the earlier work, not only because it's in black and white, and then we have many different kinds of users, not just engineers, but also interaction designers or artists, people who want to use these devices for their applications. And so we sought to try to solve this problem to support ideation and bridge between engineering and interaction design by providing a device library, haptic device library called Haptipedia. This is a project led by Hasti Seifi, who's doing my postdoc, and she's now at the University of Copenhagen. My PhD student, Farimah Fazlollahi, and Karon MacLean, who's at UBC, is the other faculty member in this project. And so what we did is we looked through more than 2,000 papers in the literature, also device spec sheets describing all these different grounded force feedback devices. And then we came up with a taxonomy for how do we describe a device like this, and then iterated. We would visualize that data and show it to different groups, experts and little focus groups at conferences. We demonstrated different versions of Haptipedia to a lot of people and iterated to a version that was published at Kai a few years ago. And it looks like this. So we have all of these different devices. There are more than 100 different haptic devices described, and you can search, you can visualize them. We have little videos. We make CAD models. Farimah made CAD models, so you can see how some of them move. You can download a lot of information about them, and you can see specifications. But as often happens, research often opens up new questions. So, we'll be done. But no, the specifications that this paper versus this paper, or this device manufacturer versus this device manufacturer, what they report is totally different. There's not a standard way to describe these devices. And so, that even the metrics that are described, sometimes they're not even well matched to what experts judge, how experts judge devices, what an expert cares about. They're self-reported, so there's inherently some bias. They aren't defined in a consistent way. Sometimes they're subjective, like what's the maximum stiffness this device can portray? Well, actually, that depends on your hand and how you hold the device and how you move. And they vary across the workspace of the device, and they often just aren't reported at all. We realized this was an even bigger problem that we wanted to solve. And so this became the PhD thesis of Farimah Fazlollahi, who's working with me. And we created a system, kind of like a precision instrument that we want to use to characterize grounded force feedback devices. So what we imagine and what we do is that people bring a new grounded force feedback device to Haptify, and it has at the center a custom-built force plate. And then we made a 3D printed handle that also has a force sensor in it. We use, let me go back. There are Vicon cameras around. Now they're mounted on the walls. This was an early picture when they were still on tripods. And we put retroreflective markers on the devices, and we gather data as a user holds the handle and moves it around in different experiments, similar to how you would test drive a car and try to standard it, like how does this car perform on the city, on the highway, in the 0 to 60 test. We're trying to define benchmarks for how to compare quantitatively haptic feedback devices so that they're not only subjective, so we can really capture what you actually feel and how well they perform. This is a paper that is under review. We did major revisions and we got very nice, really helpful feedback. So I can show you like the updated version of our results. And I'll just highlight a few things. So the first thing we do is we just measure the workspace shape. So Farimah touches the edge of the workspace. These are rotating very slowly, so you can see the 3D. So she moves around the edge of the workspace. Of course, you can calculate this through forward kinematics, and we do. But interesting things happen. Like for the upper device, which is a phantom or a touch, you can see over here, it's predicted to have this bottom lobe like this one. But on this device, you collide with the base. So you can't actually reach that part of the workspace. And there are other times where the link lengths aren't quite right or the shape is a little bit different. Another thing I think is really important is as you move around, you hold the handle and you move through the workspace. Ideally, you feel nothing, right? But you actually feel something due to gravity imbalance, due to friction. And so what Farimah does is she moves slowly through the workspace and we measure the force vector. And you can see between these two devices, the bottom one is quite a bit more expensive than the top one. There's actually a big difference in the amount of force that you feel and also in the directionality of that force. And so now we can really see that the device on the bottom has much lower and more consistently directed forces that the user feels. And this leads to a better quality user experience. The last one is we also render haptic content. So we use Chai 3D to render the same stiffness. Here we were rendering 0.75 newtons per millimeter. And then Farimah pushes just perpendicularly down into the surface and we measure what is the force that we feel as a function of position. And you can see neither device achieves the actual stiffness because the linkage of the robot is in series with the virtual stiffness. The virtual stiffness is at the motor, but the whole device is actually stretching more. And you can see that the lower device does a better job. It's like 80% of the stiffness. The upper device, it's much softer. And then so we do a bunch of other ones. We do a bunch of other things as well, looking at the vibrations and the friction in the plane and things like that. But I'm really excited about this because we can finally measure what someone feels when they're touching a device and then quantitatively say, this device is better, or if you were going to make this trajectory, what do we do some nonlinear modeling. If a user made this trajectory, what are the background forces that they will feel, and how big is that of a difference compared to the content that you plan to render? So that is Haptify, and that is the first big project that I wanted to tell you about. This is ongoing work. We're continuing. We hope it will also. We're going to characterize a lot more devices and upload the metrics to Haptipedia and also develop new metrics and validate them with experts to really make sure that we're capturing all the aspects of haptic devices that experts really pay attention to. Farimah is about to run a big study where experts come in and we record data as they use the devices and what they say, how they qualitatively evaluate the device, and that shows up in the data. So yeah. Does anyone have any questions about this Haptify Haptipedia project before? Oh, I forgot to. This is her just showing other haptic interactions that we have made. I have a second half of my talk, but if there are questions now, Kostas.
Katherine, that's a really amazing project. I wish we could do it for other stuff we are doing also in robotics. But did you choose only force displaying devices? So no pure sensors, or?
So the current plan is that that we envision there will be multiple Haptipedias, and the first one is this grounded force feedback category because it's the oldest and most mature and very diverse. There are hundreds of grounded force feedback devices that have been invented. And so we only so far have done one, but I hope we'll do it again. I've gotten a lot, I keynoted at ICOR a few years ago and there was a lot of interest in something like this for exoskeletons. I think Hasti did something like this for another category of device. I think it was in locomotion devices in VR, but I would be very happy if other people do things like this. But We could show like high frequency vibrations, but it's for grounded forces plus the vibrations that they output. But so far it's not like tactile for skin, but I would imagine, I'm interested in generally in things like that. Like being at a Max Planck Institute, I hope that we can do things like that that are good for the community and try to standardize and compare between different solutions. What Haptipedia, what I hear from other researchers is that being able to look in Haptipedia, you can actually prove, hey, there isn't a device yet that does this, that's large workspace and low force, or this, or like whatever it is, high force and small workspace, or has this many degrees of freedom. So just creating, it's not the same as a competition, but creating a way that everyone can look together and try to have the community agree. And I think we need separate Haptipedias for other kinds of haptic interaction devices. Would there be any other questions now? Please.
Thanks, Katherine. So the performance measures that you try to quantify here, is there any correlation between those performance metrics and kind of specific downstream applications that different experts might be interested in, like a person wishing to use something like this for surgery versus?
Yeah, for sure. Actually, that's something, I'm just going to go to the end of this movie, which shows the metrics that we report in this manuscript, which hopefully will be published soon. We started with the most basics, just like with the workspace and the background forces, which vary spatially, and then how well we can model those, and then the friction on a frictionless plane and the stiffness. So I think like a main application for these devices, two main applications are design, like CAD design, and that's like showing geometry and stiffness, having high stiffness and precise geometry is important, and then surgery, medical simulation. And then in both of these, you want like not high forces in free space, and you want to be able to like feel, you want to be able to trust the device that it's outputting what you say. So not only I think Haptipedia can show us like, okay, maybe there's new devices that haven't been invented, but I think we can also use this approach to optimize a particular device. So if we model how this device feels, then can I compensate a little bit, say, for its friction? Or can I recommend this content you should render in this part of the workspace? Because this is really the highest quality region where this content will be the least distorted. So there's clearly a lot of stuff that we can do. And the next study Farimah is about to run, we're bringing lots of experts, haptic experts in to spend a whole day and test 4 different devices on a whole bunch of different metrics, and also talk about applications they've designed and developed for, and which of the devices would fit that and what metrics are important to them. So that will be in the next year or so. Was there another voice? Or okay. No, it's fine. Shall I move on to the second half? Is that okay? I think we're doing okay on time, which is good. All right, so that was Haptify and Haptipedia, the first half of haptics, and now we're going to shift gears to physical human-robot interaction. And this is something that has built up in my lab much more after I moved. But I find robots very charming. I would really love them to help me in my house. They're quite different from haptic devices, because this haptic device, I think of it mostly as a tool, right? It's modulating my physical interaction. Robots as agents, social, physical, human robots, they have a personality. We treat them more like another entity. And so I have written, no one has trusted me to write an encyclopedia article about physical human-robot interaction, so you should take everything I say with a grain of salt. But it is something I'm really interested in, and I think there's not that many robots in the world that are close to humans and that are physically touching humans. Why? Okay, well, they can't feel, most robots. It's not easy to make them safe around robots. Robots are often designed and built to be very stiff, but we want like more soft, back-drivable, inherently safe things moving around people. And their whole social dynamics, not just the physical dynamics, but there's like social dynamics. People can get offended by this robot and think it's rude. But I have started thinking about physical human-robot interaction in a simple way. I try to categorize interactions in 2 ways. So what are the body parts that are touching between the people? And is it something that's event-based, just like short-term, or something ongoing, like continuing? And so you can imagine between a human and a robot, like a hand-to-hand contact, like I'm going to give you a high five, or maybe we're going to hold hands or shake hands, or maybe there's a tool. We just had an pHRI paper on handing tools from robots to people, and how can a robot do that in an effective way? Or maybe we're jointly manipulating an object together between a human and robot. Maybe the robot wants to get your attention, or comfort you, or massage your shoulder, or maybe I'll show you our hugging robot. The only event-based body, full body interaction I think of is a full body collision, inadvertently walking into a robot in the hallway, which I hope it doesn't happen. But if it does, the robot should be able to feel that it did crash into you and react appropriately and say it's sorry. I will just show you some sample projects and maybe they will pique your interest. This work I started in robotics before I came to Penn. I had not done like any work on autonomous robots. And it was my first PhD student, Joe Romano, who, while he was working on haptic textures and other haptic devices, he got really interested, inspired from other people here in GRASP on autonomous robots and how to give them a better sense of touch. And so Max Likachev and I had written, and others in GRASP had written a PR2 beta proposal to get a PR2, a personal robot too. And Joe went and interned at Willow Garage. And this is work he did there. We published in Transactions on Robotics on using the very basic tactile sensors that a PR2 has to pick up objects that it doesn't know about and hold objects that are changing in weight and react. So we mimic the tactile cues that are known to be important in human touch, which is especially a focus on transients like changes, like when I'm setting an object down or when I'm holding something and it slips in my fingers. Those are events you want to be able to react to and respond to that the robot needs to handle. And then Joe also programmed this demo just for fun on the side. And I would say you should do fun things on the side when you have time, because sometimes they lead you in really new, interesting directions. And so he programmed the PR2 to do high fives and double high fives. And they said, oh, and I made fist bumps, Katherine, and fist bump explodes. So this is called PR2 props, and it's been shown like to thousands and thousands of people, to kids and all around the world. And it's actually really fun. And it's so simple. The robot just moves through a trajectory and it's feeling on its accelerometer in its hand and on its tactile sensors for a contact, and then it pulls back and stops. And that would be hard to do with vision, to detect it well and have it feel interactive. And that got us started on lots of things in human robot interaction and how touch can enable new kinds of physical interactions, because you really want the robot to be able to feel you and respond to you. And that feels like you've made a connection with the robot. And then my fifth Penn PhD student, Naomi Fitter, got really inspired by that demo, and her whole thesis was on hand clapping between robots. And so this is with Baxter. Actually, Kostas thinks this is your Baxter robot. You let us use it. Thank you very much. Yeah, so we tested all sorts of things like keeping rhythm with the robot or adapting, and people notice if or people like the robot better if it smiles at impact. And then for the last part of the thesis, Michelle Johnson was on Naomi's thesis committee. She said this could be really helpful for rehab. And I'm still working with Michelle on this, and also my, at the time, a master's student with Michelle, who's now a PhD student with me, Mayumi Mohan. We used Baxter to bake a bunch of exercise games. And so I call these are like little apps for Baxter, or hopefully they could be adapted to other robots. And most of them involve physical contact. So we programmed 6 games, agility, strength, hand clap, and I'll just show you agility. This is a demo in my lab at Penn. The robot is asleep. You have to wake it up by hitting its hands repeatedly for like more than a minute. So we're trying to fool you into exercising, doing something active, and have it be fun. And it actually works really well. You just tie a little bit of a story, a little bit of sound, a little bit of facial expression, and people actually really enjoy playing these games. So then we also made Mimic. There's ones where you're hand clapping or you're reaching and you're making music with the robot. And then we also programmed 2 games that don't involve physical contact. And these are more typical, similar to some apps other people have programmed. So I'll just show you Roboga, which is like robot yoga. And here the robot like makes arm movements and you have to like copy it, but actually the robot has no idea what you're doing. And then you mimic it. And so you are together doing these exercises. And so we brought 40 people into Michelle's lab in downtown Philly. 20 younger adults and 20 older adults, and have them try all of these games in different orders, random orders, and choose their favorite game. And it was actually, people really enjoyed these games much more than we expected. They're from the beginning, when they first met the robot, till after they'd had all these interactions, their trust and confidence greatly increased. And then only the red games, the games that had physical contact, where it fell into the highest ranges for what people thought were pleasant or enjoyable or engaging or cognitively challenging. So people found these gray games rather boring, the games where you're just like mimicking the robot, and especially because the robot didn't know if you were doing it. There was no feedback. There was no compensation. A robot didn't know. You could cheat. You didn't have to do what the robot wanted you to do. So that was a lot of fun. We're still doing a little bit more analysis on that, on those exercise games, more on the qualitative feedback, but it was really a delightful project. And then another PhD student collaborated also with Michelle. I just wanted to briefly show you this. This is also with the PRT. This is a therapist on the left and a patient with stroke on the right and who has upper limb impairment. And what we did is the therapist is teleoperating the robot from right to left arm. So the right arm is controlling the left arm and cooperating with the patient to do, in this case, a figure-8 motion. We also did up and down and like a pick and place motion. And then from the data that was recorded of how the therapist guided the patient through the exercise, then the robot can repeat that. So we learn a simple mathematical model, like predicting what force the robot should exert based on the state it's at now. This was published in RAL last year. And then the patient can just do more and more and more and more. We also had the therapist try the exercises, and she really liked, the patients and the therapist really liked, this is the figure-8 motion of the robot, her showing doing the figure-8 motion that was recorded. And they really like the feeling. It's like gives you more control and autonomy and kind of makes you work harder and it can adapt. And compared to like just following a trajectory passively, it's like we'll help you, or you can see the kinds of trajectories that we got. Okay, I'm going to skip. I don't have time to go into all the details, but I wanted to at least mention that because it was really, and that was the study we were running when the pandemic hit. So luckily we ran 6 patients before everything got shut down. And then we said, okay, we'll publish the 6 patients and Nick will graduate and go work at Amazon Robotics. But it was a really nice cooperation. All right, so now the last project I want to tell you about is HuggieBot. And this is the biggest thing we've been doing in physical human-robot interaction. You might have already noticed this, but hugging is very good for you. I recommend you get 8 hugs a day if you can, or more is even better. So getting a hug means, of course, wearing a mask or being safe. It provides you social support, it increases your immune system, it raises your oxytocin levels, which is like the love hormone. It makes you, gives you more positive emotions, reduces your stress, and lowers your blood pressure. So physiologically, physical contact with other people has a very positive impact on you. Now, if you are in a situation where you can't, let's say you're locked down or you're in quarantine for 2 weeks or alone, away from your family, you just moved to Germany, you don't know anyone in this new city you just moved to, it becomes more likely you might become sad or depressed or have mental health problems, low self-esteem, your pain thresholds go up when you don't have physical touch. And especially if you, as a child, as a baby, you didn't have much physical touch, you might even later have more difficulty forming relationships. So it's known that touch is important, but there are situations where we can't get a hug from a human. And so Alexis and I, for her master's thesis, we decided to turn the PR2 into a hugging robot. And this is her master's thesis research, where we put the PR2 in a warm, fuzzy, soft outfit and had it hug participants in different ways. And we learned, there was a behavior, or there was a physical part of this study and a behavioral part. And that video, most of those videos are up in Levin. And so first we tested a hard cold robot, and then a soft cold robot, and then a soft warm robot. Everyone prefers the soft warm robot. It's much more comfortable to hug. And then in the behavioral aspects, and I'll show this video on the bottom right. Oh, I should go back. Sorry, it did start on its own. The video on the bottom right, it's a little subtle, but we programmed first if the robot would kind of air hug you. People don't like that, or hug you just right or tight. That's also good. But then we programmed it so the robot hugs you and then lets go immediately. People don't like that very much. That's perceived as a rude robot. The robot hugs you, and then right when you signal you want to let go, it lets go. That's great. And then we programmed the robot that holds on too long. 5 seconds after you have said, it just keeps holding you. And people really don't like that. So robots need to let go of their hugging partner when their hugging partner indicates that they want to stop hugging. So this was Alexis's master's thesis. It was a lot of fun. And then for her PhD, she came to Germany, and she was in our co-advised ETH PhD program called the Center for Learning Systems. And she designed and built and programmed a new HuggieBot, completely custom. So we took 2 Canova Jacko arms on a V-shaped base to make it very easy for you to come up. It has a head that can show a face. The arms have torque sensors, and then she made an inflated torso that's soft and warm, and we put a pressure sensor and a microphone inside so the robot can feel as you're holding it and hugging it. And did a lot of, there's also computer vision, there's an Intel depth camera. And so this is HuggieBot 2.0. So this was published at pHRI last year. In the bottom is participant videos of people hugging this robot. It's soft, warm, it's quiet, it sees you and reacts when you want to come over, it adapts to your size. So we treat hugging like a grasping problem, like a two-fingered grasping problem. And we wrap around you and stop. So if you're bigger or smaller, or over to the left or over to the right, you always get a comfortable, nice embrace. And then when you lean back against the arms, yeah, she's really enjoying that hug. Or if you let go of the robot, it lets you go right on time. And it's really actually much more fun to hug this robot than you might imagine from just watching the videos. So that's HuggieBot 2.0, but I mainly want to tell you about HuggieBot 3.0 because during this study, we noticed that sometimes people would pat the robot on the back or squeeze it. And so we wanted to augment the robot's capabilities to be more, when you're in the arms of the robot, to be able to have like a haptic conversation with you. And so I should have said, yeah, some of the co-authors, Otmar Hilliges and Roger Gassert from ETH were Alexis's co-advisors, and Hasti Seifi was also involved in this work. So we defined 4 different intra-hug gestures. So the first is just holding, being quiet and calm. And then you could squeeze your hugging partner, you could pat them on the back, or you could rub them on the back. So we gathered a big data set from the microphone and the pressure sensor. So only 2 channels, 2 analog sensors over time. But you can actually see a lot of signals. So this is one participant demonstrating. You can see the purple, the patting, this person patted very, very violently, squeezed really hard. Other people were much more gentle or slower. We gathered a lot of data, and then in real time, we take little windows of that data and we do simple machine learning, just a random forest classifier that we supervised ahead of, that we did supervised learning on ahead of time. And then the robot can perceive or guess what is happening to it. I know, oh, the user's squeezing me or they're patting my back. And we can do that very well on previously unseen natural data in ambient conditions that are messy. So the robot has a pretty good idea of what is happening, especially if you squeeze it, it really will recognize. But then an interesting thing is, what should the robot do in response? So imagine you're the robot and you feel the user just squeezed you. What should you do? So we originally thought that the robot should reciprocate. So if I'm hugging Mark and Mark is holding still, I just hold still. And Mark pats me on the back, I pat him on the back. That's what we thought people would like. But we said, maybe that's not what people will like. Maybe people don't like it when a robot pats them on the back. And so we wanted to find out. So we exposed people to all 16 possible combinations. We had them hug the robot and said, okay, this time you're just going to hold still and the robot is going to rub your back. Okay. And you're going to get a sense of what that feels like. Or you're going to pat the robot and the robot's going to do nothing in response. And you're going to tell us. So on the y-axis of each of these, you can see pink means I love it and blue means I hate it. So people generally like hugging robots. And you can see when the robot did something, people really liked it. The only thing people don't like, or many people don't like, is if they do something, like they squeeze the robot and it does nothing in response. Again, they feel like this is a non-responsive, non-socially smart robot that's like incapable. It makes sense. We don't even need sensors. Like if the robot knows that you did something and it doesn't do anything in response, well, it's kind of a missed opportunity. But what we thought was really surprising, we expected up on the right where you were holding and the robot is proactively patting or rubbing you. We didn't think people would like that, but people loved it. They said, the robot really cares about me. The robot likes me. The robot wants me to be happy. Like alarmingly, like a huge number of people really liked it when the robot would squeeze them, especially squeezing. And so we did not at all see evidence of this diagonal that we imagined. And so this, I think it's good to actually test things. There haven't been many hugging robots, like almost none that can do this kind of thing before. And we said, okay, what's going to happen? And then we took this data and we programmed a simple probabilistic algorithm to basically trade off between some variety, but favoring things that people tend to like and providing some variety, because that was also something people talked about a lot in their comments. And so this is now HuggieBot 3. This was recently accepted to pHRI. I didn't realize that we can move that to the bottom. I don't know why it's showing that. I'm sorry. Has that been there the whole time? I'm sorry. There, that's smaller at least. Yeah, so this is a participant in our study, and he's patting the robot, and the robot's feeling, and he's responding. The best place to see is here. This is where you can see the robot squeezing. Okay, now the hug is over. And he's going to go tell us what he thought about that hug. Okay, now here's another, you can watch, it's really fun to watch participants hugging the robot. Here's another hug of a different participant. The robot also sees if you're taller or shorter and adjusts to that. And getting the timing right definitely required decent computer vision. And then in this study, you see we had people do these intro hugs and had them rate the naturalness, enjoyability, intelligence, and friendliness of the robot. And then they did a bunch of the other data collection. And at the end, they got more hugs. And you can see we saw significant increases in naturalness, enjoyability, and intelligence over the course of the study to very high levels. The robot was always perceived as friendly, both before and after the study on average by all the people. And so I think these intra-hug gestures really improved the quality of the interaction that people had with the robot. So that is what I wanted to tell you about physical human-robot interaction and HuggieBot in particular. I want to just sum up with a few overarching themes. I'm almost done. You might notice that physical hardware and mechatronic integrations can definitely be tricky. This is, I think, why it's important to be working interdisciplinary and collaborating and have some good support. I gave a Coral tutorial 2 years ago on debugging interactive haptic robots and talked about a lot of tips and tricks that I teach my students for how to get robotic systems to work well. And so if that's interesting to you, you could check it out. These closed loop, so although humans can feel signals, although people can only output motion up to a couple hertz, we can feel tactile signals up to 1,000 hertz. So the feedback that we get should match that, especially in hard surfaces, textures, tool-based interactions. Robots, when we're sending them out into the world to be around people and do useful things, I think they need broad bandwidth haptic sensing. We're also working on haptic sensors that can cover the arms and bodies of robots, on fingertip haptic sensors with different mechanisms. But this torso that I showed you for HuggieBot, it's super simple. We have no idea where the user taps or pats, but we can still know what they did. And in that context, that's really sufficient. That's all we need. And yeah, people vary a lot in their size, their shape, their personality, their preferences. So I think it's really important that we test these interactive systems with humans. We always have ethical approval. We always do informed consent or have a waiver of consent. So I think I would encourage you, if you're creating any technologies for people, that doing that is really important and you learn a lot. It's a lot of work, but you learn things you wouldn't learn if you only hugged your robot, right? And something I see in both the domains is like we need good contrast between the content, what we want the user to feel, whether it's this virtual object or the contact that the robot is having with the virtual environment or the pat on the back, and the background noise, the things, the other things that I feel when I'm moving through free space or when I'm holding the robot. Like we want good contrast for perception. All right, and that's it. This is my team from showing them how we looked in October without our masks on before things locked down again. And I want to thank you all for your kind attention. I want to thank the organizers, the Grass Lab, I'll say really fast, and people who've reviewed our papers and written letters for me and my students, the funding agencies, especially the Max Planck Society, all of our wonderful collaborators, mentors, including Max Vince, and friends and family. And with that, thank you very much.
That was fantastic. So we've got, I just want to remind people that are online, if you've got questions, type them into the Q&A and we'll get to them. But before we get to the rest of we've got 15 minutes for our panel. I'd like to introduce our panelists, Laura Halleck. Laura is currently a postdoc working with Vijay Kumar and Michelle Johnson. She's a recent PhD graduate from Berkeley from the Baichi Group. Her research area is in novel musculoskeletal sensing and modeling for improved human physical robot collaboration and robot-based rehabilitation. Thank you for that. Letting me say that, big mouthful. Anyway, hello, Laura.
Hi, Laura. Hi. Well, I guess I will take my prerogative and ask you the first question then. I guess I'm interested, you first of all, I think the Haptipedia is great. I think we need more systematic, I guess, systematizations generally of the technology that exists. I'm curious sort of on the, I guess that's mostly for these sort of force feedback grounded devices. I'm curious, as we move toward more, so these more wearable devices where we might not be able to generate this, exact mapping via force feedback using things like vibration, what technologies in this area are you most excited about?
Yeah, so we work also in wearables and in screen-based interactions. I think we're exploring a lot of things. I still believe in electromagnetic actuation. It's often what we're using. We have a paper that we're revising for soft robotics now that's using like a soft finger sheath and a magnet and electromagnetic field, because you can just have really high bandwidth. So you can like really deliver very nice waveforms to the skin and feel that. But we do some modeling of the finger. So understanding the skin is different at different points on the body, the kinds of receptors you have. I believe that like for fingertip devices, your finger and my finger and Mark's finger and Kostas' finger, they're all different. We all have somewhat different skin properties and sizes also on other parts of our body. And I think so far that hasn't been considered very much we often just play signals, open loop, and just assume that something will get through. But if we want to precisely deliver signals, no matter what the technology is for the wearable device, I think the way it's attached to the body and then like how it's applying the signals to the body, I think we can do I really believe in sensing and like measuring what is actually happening and then using that to maybe make signals feel more different or feel from one another or more similar from person to person. So I guess I don't have any particular one technology that I believe in. We are using vibrotactile cues I have a project with Annie Hallilai at Carnegie Mellon where we're working on trying to help people with wearable sensors and wearable actuators modify their gait to walk in a more healthy way for their knee. And we are using vibrotactile cues there. In other scenarios, we're looking at shape change, things you feel in your hand, or contact, making breaking contact. So we work on many things. In screen-based interactions, we have done some work on various technologies that either reduce the friction of your finger across the screen or can increase the friction of your finger across the screen. I think they both have promise. We're working more on the second one on electrovibration, try to understand the mechanical and electrical contact between the finger. And again, I want to measure what actually physically happens so that then we can make it feel more like a real texture on the screen. But I don't have anything to show on that yet.
1,000 more questions.
Sorry
but I
about
don't wanna
that.
Dominate the room.
No, you're good. Thank you for asking. I guess I'm technology agnostic and I'm always interested in new ideas. Please.
Thank you, Katherine, for the fantastic talk. So I have a question about the HuggieBot. So for me personally, it really depends on the situation, how I feel about a hug. If it's for courtesy and if it's like someone I'm not close with, then a squeeze might feel more like awkward than love.
Yeah.
So I'm wondering what is underlying the psychology in these experiments. So why is like squeeze preferred than other modes?
I think there are two reasons why the squeeze is preferred. So the context is absolutely critical for human-robot interaction, human-human interaction. And the context that people were told was like, they knew they had signed up for a study about hugging robots. They were curious about that. And many of them, they particularly said because of the pandemic, this was done during lockdown, they hadn't had hugs in a long time and they knew that was affecting them. So they were sort of people, we were naturally selected for people who were interested. And I think many people hug the robot for more than 20 seconds. A typical hug between acquaintances is like 2 or 3 seconds long, very short. And people often chose to hug the robot much, much longer than that. And I think they kind of figured out, especially as they grew comfortable with it, that it was comforting, that it really like calmed them down. We have another study that we haven't finished analyzing yet where we purposefully stressed people out. And then, well, they had to give a little, it's an ethically approved, like a standardized way to stress people out, calls the Trier social stress test, where I'm serious. And we tell you, okay, you have 5 minutes to prepare a presentation on why you're the best candidate for your dream job. And then for another 5 minutes, and then you give that presentation in front of a panel of stern looking actors who are judging you. And then you have to count backwards from like 1013 by 7 and successively. And then when you mess up, we buzz a buzzer and you go back to the beginning and do it again. And then you were randomly assigned to one of 5 conditions. You were assigned to HuggieBot with giving a good hug, HuggieBot with like not very good, like an air hug, hug a human, hugging like a human, so or hug a human hugging like HuggieBot, or to stand in an empty room alone. And yeah, I shouldn't say too much because we haven't analyzed this, but I think the context that we're thinking about is maybe this robot is in the lobby of a building and you go get a cup of water and you go get your hug, and it's like a self-care, or you sit in the massage chair or you get a care. And so I think it's pretty fundamental. And if you're choosing, we always let the person choose. We're never forcing hugs on you. Like, it's always up to you. And then when the robot, in that context, when the robot squeezes, it feels good. The second reason why I think is just physically the robot is already in contact with you and it's just increasing the contact, whereas the padding was a little jerky, like a little robotic, and the rubbing was also just, it wasn't quite as smooth, or this felt like very embracing and like generous, but like the padding and rubbing, the robot is too stiff, unfortunately. It's not back drivable. And so we're doing kind of like open, it's soft and we have torque sensors, but it's not doing torque control. And so it's like a little bit, it's like in a moving cage, but somehow the squeeze, because your body softens it, it feels better. Oh, but interesting, people with very low body mass index, so very, very skinny people, they don't like it when the robot squeezes them because it hurts them, because they don't have enough padding. Alexis and I are like normal weight and we always felt good. And we had some very, very thin people that hurts them. So the robot should be even more padded when hugging very thin people. You're welcome.
Super interesting. We've got a question online from Professor Kuchenbecker. Thanks for the very inspiring talk and such exciting work, Katherine. In the Haptify project, you started to systematically develop metrics for devices and control architectures. Coming back to the earlier question about developers of user experiences for these devices, do you think it is feasible, easy, hard, super challenging, to begin to develop measurable dimensions to characterize the various task domains for these machines?
The various task domains for these machines. In terms of checking the applications that they would be used for, or I think I don't understand the question. Could you say the key part near the end one more time for me? Do you think it's easy, hard, or?
Do you think it's feasible, easy, hard, super challenging, to begin to develop measurable dimensions to characterize the various task domains for these machines? Okay, Dan has a follow-up. No, what range of jobs are in mind?
Range of jobs are involved for the devices. I do think that applications for haptic devices, especially if we constrain ourselves to grounded force feedback devices, there are certainly, like, there's medical simulation and training, there's CAD, there's teleoperation, there's learning physics. So it is definitely, there are different applications where these devices might be useful for, and you can evaluate a particular device for each of those, and it often comes down to the degrees of freedom. That's like the first most basic thing. It's like, what kinds of motions does it afford? Like the input degrees of freedom and the output degrees of freedom. And that actually is how the experts organize devices. We had a second Kai paper. We had experts look at Haptipedia and show pairwise cluster the devices. We found they tended to cluster mostly by the degrees of freedom, which is basically like what kinds of interactions a user can have. Is it only a planar device? Is it 3DOF without orientation? Is it 3DOF with orientation? Is it a large workspace device? Is it like weird, like for your foot? So that's like body part and motion degrees of freedom.
Does that lead toward application? I think it's
and I think that's the main thing that leads into application, because an application, you often know, okay, the user needs to control, it's only a 2D task, or they have to do 6DOF control of the robot or more than that. So I think it comes down, and that's how the experts sort the devices, which is how they're now organized on Haptipedia.
Thanks again for the really wonderful talk, Katherine. Do we know how much of the physiological or social or developmental benefits of hugging and other social behaviors actually transfer to replicating these behaviors with robots?
That's a great question. And that's actually the other half of the study that I told you about. So not only did we had them wear a heart rate monitor, and we took saliva samples. So during COVID, during lockdown, we had people come into our lab and spit into little vials so that, but while we stressed them out and after we stressed them out and after they hugged our robot, so that we could measure their cortisol, which is a stress hormone, and also their oxytocin, which is that love hormone that tends to increase when you're hugged. And we just got the results like a week ago. So it looks like it's not the same as hugging a human. Like we can't pass the Turing test for hugging robots, right? You hug this robot, you know you're hugging a robot, you know it's not a human, but it does have a physiological positive impact on you. It does seem to increase your oxytocin, and that matches a lot of the positive feedback we have. So imagine you're a college student going to university away from your home with parents, or you are a patient who can't be near, you have an immune compromise, and so you can't be near other people. And so being able to get some physical comfort like this could be beneficial. The unexpected thing that I didn't imagine, I thought the people would love the human most, but actually they felt a little uncomfortable hugging the woman that we hired. She was a very good hugger, but they felt guilty having a really long hug with her. They said, I feel bad. Maybe she doesn't want to hug me this long. Like, you hired her to hug me, but like, maybe she doesn't want to hug me, maybe, and they could feel her breathing and hear her breathing and feel her heart rate. And so people actually, because the people in the human hug condition first, they also got to hug the robot because we wanted that comparison. And many people really liked hugging the robot even more because there wasn't this social pressure. But I mean, clearly human hugs are great when you know the person. I think hugging a stranger or an actress hired to hug you versus hugging someone you know and love is a different experience. Yeah. Kostas also has a question.
Yeah, exactly.
Katherine, very nice to see you again, and it was a wonderful talk.
Thanks.
In this closed human-robot interaction, first question is, did you add any sensors to these robots? And if even if you did or did not, what do we miss on the sensing part for the robot? I mean, we could have a camera observing the facial expression or something like this, but in the actual haptic part, force part, what is missing?
Yeah, so currently we have a depth sensor, an Intel depth camera for the distance to see there's a person, to offer a hug and to know when they're coming. But the robot's actually blind. Once you come pretty close, that camera can't see you anymore. We can't see their face. They can only feel, the robot can feel the user. And it's extremely simple. We have the torque sensors built into the arms and we monitor the torques during the hug, only for like, if it's time to go, like it's super simple. And then we have a pressure sensor and the microphone in the chest. And that's what we're doing the gesture detection on, and also the release. I think there's a lot more. I actually don't think the sensing is currently the limiting factor. I think the arms, I really wish they were back drivable and like more soft and gentle. And then what would I want after that? Yeah, being able to automatically, it's self-report like questionnaires. It's never fun for the user. It would be great if the robot could see their facial expression and learn from that and adapt to them. I think there's also really big variety in how different people hug, and yeah, like that we should customize more for preference, but we're not doing that yet. Alexis graduated. She's now a postdoc at UCLA with Veronica Santos. She won the Otto Hahn Medal, which is the Max Planck Society's prize for PhD theses, and she's a computing innovation fellow. So she will apply for faculty jobs in a couple of years or a year. I think she will continue making more hugging robots. I probably will not work on that anymore to give her space to make her name, continue making her name in hugging robots.
One more question online. Kind of along the hardware. Just real quick. What's the most promising method of
What is the most promising method of actuation for wearable haptic devices? Well, we have a new director in our institute, Christoph Keplinger, who used to be at the University of Colorado Boulder, and he invented these Hazel actuators. And I have a couple of collaborations with him where we're using Hazel actuators for haptics at the fingertip and wearable, and it seems to be going pretty well. It's very high voltage, so thousands of volts, and so the safety aspects are tricky, but compared to pneumatics, it's really promising because it can all be wearable and you can walk around. You don't need like a giant pump. It's just a battery and a little bit of electronics, and then locally it can make really interesting sensations. So we're exploring that, but I still think electromagnetic actuation, like voice, I particularly like voice coils, not like eccentric rotating mass motors, because when you have an eccentric rotating mass motor, the frequency of the vibration and the amplitude are coupled. It's like annoying and it grabs your attention. It's fine, but it doesn't, it's not like, it doesn't match real physical things that you feel. So when you can independently change the frequency and amplitude, that's still what we tend to use. But something I'm like kind of interested in, but haven't used at all, is where you're actually applying electrical stimulation to the skin. I've tried some demos, and it's very localized and salient, but not natural, but maybe in some cases, and it's super low profile. So it's just like electrodes printed on your skin and zapping your skin. And so you can get local, like temporal, quick and local, but it's not that comfortable and it doesn't really feel like natural stuff. But I think for some applications that could be really good. Those are some quick ideas. Yeah, please.
Yeah, so I have a question about the schematic of the haptics that you showed earlier. So I remember there was no interface between processors and virtual environments or physical environments, but I would imagine that was sensor that you use to pick up what the object feels like is important to what you convey to the user. Yeah, right there.
Yeah, I do have it that like, so the left side is like what we're getting from the user, and then those like bidirectional errors from the remote environment or for the user for the virtual environment. It could be both as well, but yeah, we are getting sensor data from the environment you're interacting with and feeding that back.
Oh, okay, yeah.
No, that's definitely critical. Sorry, that wasn't clear.
Right, so I thought that was like a design decision or something, but yeah, that makes sense. Yeah.
I think what I think is different here is like what my sort of philosophy is: the remote environment is a virtual environment, and also part of all of my tangible surroundings. So what I'm trying to emphasize is that the device itself is the main thing the user feels. And this is, I think, sometimes why bad haptics is worse than no haptics, because you're encumbering the user, it's complex, it's expensive. So the benefit of the haptic cues has to outweigh the encumbrance and the cost of the device. And so there's like a really good balance. And we're not nearly there compared to like audio or visual presentation of haptic feedback, of feedback. But I think you have to keep both of those in mind. And certainly the data we get from the remote environment, the virtual environment, heavily influences what we present to the user and how their emotions are responded to, certainly. Yeah.
I think that's it. Let's thank our speaker one more time.
Thank you very much.